as you are a student now up to year 3 in the curriculum, you may have already built up your taste about textbooks. So therefore, and that's why I list a long list of books here. I hope that some of them will fit your taste. So I have separated them into different categories. The first category emphasizes more on the physics side. Okay, so quantum physics books. And then I list a few of them. And then they are excellent authors, I would say, and explain the physics really clearly. I also wrote some comments if I have read them. And then down there, I have listed some quantum mechanics book, meaning more on the formula sum. I think you have used Griffin's book in the previous course. Well, refer to that. And then I list several others that some of them have more formula, some of them have more explanation. Again, it is your taste. Further down, I list some more specialized books into a topic. So atoms and molecules, I have list some quantum chemistry book. This particular book by McCurry is very nicely written for actually a beginning postgraduate level of quantum of chemistry students. Nonetheless, for physics students, it is quite at the right level, and it is very well written. And then if you want to learn very seriously atoms and molecules, the book by Blanston is also very good, many equations. And then Christopher Foote, atomic physics, this one actually is often used as a master degree level textbooks on a course on atomic physics. I also list some nuclear physics books and solid state physics books in case you want to make use of your quantum mechanics knowledge and to understand these two topics. And then I also list some mathematical skills book. They are survival guides. And I don't list those that are thick dictionary-like. Instead, I picked two that I think were wonderfully written, short, and the authors try to explain the mathematics to you rather than many formulas. Okay, so the first one is actually written for chemistry students, the chemistry maths book. I think it's a wonderful thing because the author collected all the mathematics that a students need to complete a BSc degree in chemistry. I hope that you understand that in chemistry, there's a branch called physical chemistry. And physical chemistry consists of several topics. Thermodynamics, you know, statistical mechanics, some of you know, quantum mechanics, we are doing, and you just did that, okay? And kinetics, that physics students don't know that too much. It's about equation, the left-hand side to the right-hand side, how fast it goes, and then the right-hand side go back to the left-hand side, how fast it goes, and balance, things like that, okay? So chemical kinetics. So you see that physical chemistry overlap much with physics, okay? And therefore, the mathematical skills one needs is actually have a strong overlap with the mathematical skills that physics students need. So, and I think it is a wonderful book, especially if you want to review or learn a particular skill in half an hour. Everything is written in 3 to 4 pages. That's it. for example, eigenvalue of a matrix. You go into the first book by Steiner, 3 to 4 pages, the author explained to you what they are with examples, okay? The second book is also wonderful, longer chapters. The title already said what it means. Or you wanted to know about mathematics but were afraid to ask. The topics covered are not very fancy. For example, partial derivatives. Okay, you need partial derivatives in thermodynamics, partial U, partial S, partial U, partial T, things like that. So very often, maybe you forgot the real meaning of partial derivatives, and this book can explain to you rather nicely. It is I think it's an Oxford University book in which those students need to go to their tutor in the college every week, and then the author detected some common deficiency in the preparation of those students, and then he wrote this book. Okay, the last book is like a dictionary, 1,000 pages. Okay, with 1,000 pages, then they cover all the standard thing and beyond that a physics undergrad degree or even postgraduate level mathematics coverage. So you can try to look up the books in this list by yourself. So now it's time to motivate our course better for the first module. Sorry. Right? Okay, so you see this, the first page clearly, right? Okay, so this part, I just would like to motivate why we need to learn some approximation methods. Clearly, very simple. Many problems we cannot solve exactly. That's it, done. Okay, I would like to show you that after realizing that, there is some hope that we can develop some approximation skills. Okay, so the first two things we will do in this course are, first, do something exact. We will turn a Schrödinger problem, time-independent Schrödinger equation problem, into a big matrix, usually infinite by infinite. Okay, that is to say nobody can do it yet. But this way of turning a differential equation type problem into a big matrix problem becomes very useful for some of you who know how to do computing, because you can call subroutine to handle rather big matrices nowadays easily. Okay, and the second point is that after you have this matrix version of the problem, you can think about the approximations that follows rather easily. The second part of the first chapter is that we will develop two approximation methods. The first one is variational method. The second one is time-independent perturbation theory. After that, we will apply it to atoms, molecules, things like that. So I would like to motivate the module first. Why do we need approximation methods? Okay, so simply put, we cannot solve many problems. Although that is the key point, we know the governing equation. Now, this is very often a very often situation in physics, right? Einstein equation. We know the equation, but usually you need to do numerical general relativity, because that set of equation is just so hard, too hard to solve anything analytically. Okay, so it's not that we don't know the physics, we know the physics. By that we mean we know the governing equation. In our context, we are looking for what are the allowed energies in an atom, what are the allowed energies in a molecule, what are the allowed energies for electrons in a solid, for example. And that is perfectly suitable for applying the time-independent Schrödinger equation. Okay, I will use this TISE to abbreviate time-independent Schrödinger equation. So the point is that we know the physics, the equation, but we can't solve the equation analytically for most problems. That sets up the stage. Either we give up, of course we won't, or we find some way to solve the equation. Either you can do it numerically. If you do numerical problem skillfully, the solution is approaching the exact solution. Okay, that's why there is a branch called computational physics. In addition to theoretical physics and experimental physics, computational physics is the third branch of physics. Because very often we know the equations, but we need to solve them in some other way, numerically, for example. Here we are not doing computational physics. Instead, we will make some approximations in order to make the problem solvable. Of course, the solution will not be the exact solution. Nonetheless, that will give us good physical sense of the problem, how to think about the problem, okay, despite the solution is not exact. So we will do much here in this course. So just some example. In the previous term, you have learned to solve these problems. The first one, particle in a box. All right. So I wrote down the exact solutions. The first line are the eigenstate or the wave function. And the second line gives you the allowed energy corresponding to the particular wave function, the eigenstate phi n. Okay, so you see there's a label n, labeling each wave function with its allowed energy. They come into a pair. All right, that is what the Schrödinger equation can do for you. It is one equation that usually to be solved for infinite pairs, phi n, en, one-to-one correspondence. Okay, so give you many solutions. One equation, many pairs of solutions. So I hope that everyone knows how to get this, okay, in 2 minutes. That is the first problem in quantum mechanics, all right? And better still, if you know how to do the 2D and 3D versions of this problem, that will be nice. Because if you know how to do that, then you know what is the separation of variables method. That is a very important skill to go on in solving other physics problems. The second problem I would like to write down is the harmonic oscillator. So this is the potential energy function confining the particle. So you have the Schrödinger equation, the kinetic energy part plus this potential energy function. There's an omega 0 governing the curvature of the oscillator. Okay, so omega 0 is bigger, so it goes up faster, it's smaller, it's like that. Okay, so but nonetheless, it is quadratic, x squared. This problem turns out to be solvable exactly, and I think you have done that in the operator method, isn't it? Or you have done that in the wave function method? Both. Wonderful. Okay, that's why I said Professor Liu prepare you better than I did before. Good. All right. So now in the wave function form, after it, well, actually both ways will give you the same answer, of course. You will have this energy eigenstate. Okay, so that's a Gaussian. Suppress things down farther from the potential's center. And then there is something called the Hermite polynomial that you can look up what they are, a special function. And then there's a normalization in front, just normalize the probability density, sum up everywhere to 1, okay? And then the corresponding energy for given n is n h bar omega 0 plus the ground state half h bar omega 0, all right? So that's nice. Again, if you know how to do the 2D, 3D version, that will be even better, okay? That you can do it in two ways. You can do it separation by separation of variables, x, y, z, or you can invoke other coordinate systems. For example, in 3D, you have, instead of x squared here, you have x squared plus y squared plus z squared, isotropic 3D oscillator. Therefore, you can try to use spherical coordinates. Your solution will invoke spherical harmonics, YL m theta phi, all right? So both ways, of course, that is just the path to get at the solution, all right? The solution will remain, of course, identical in both ways. So now with that, let's motivate why we need approximation, okay? So we just wrote down the solution to this infinite well problem. We are happy about that. We know how to solve it, okay? So now how about this one? I have a rough, not a constant potential energy value inside the well. Instead, there's something rather ugly, all right? Now, again, you see, we know the equation. We can write down the Schrödinger equation, but we can't solve the equation exactly for the eigenstate and the eigenvalues. And how about this one, more regular? An infinite well, inside the well, the potential energy is a linear function of space. Now, this is a physical problem that models something like if the particle trapped inside the well is charged, and if you apply a static electric field, then you will have a linear electric potential. Thereby, times the charge, you will have a linear potential energy. Like So can you solve this one? We know the Schrodinger equation, okay? Depending on who you ask, okay? If you ask Professor Liu, then he said, I can solve it exactly, okay? So as if you ask Professor C.F. Low, okay? Or some well-trained student in mathematics. Nonetheless, even if you can solve this problem analytically, the solution will not be very transparent in terms of the physics content. The solution has to do with something called Airy function. Okay. Nonetheless, it's not very physically transparent what is going on. So we see the following situation arise. We have a problem that we can solve exactly. We are happy. Then we have many problems nearby, the cousins of that problem, that we cannot solve exactly. Now, think like a physicist. That is a big part of our course, okay? How about this? For problem B, just by looking at them, you may have this feeling already. The nth eigenstate of this problem should not be very different from the nth eigenstate of the exactly solvable problem A, right? Okay, so with that idea, we started to think, perhaps this problem that we cannot solve, the nth eigenstate, may be the solvable known value of problem A plus some corrections. And these corrections must due to this thing, and how far this thing, this rough bottom from this flat bottom of the solvable problem, the deviation in the potential energy function, okay? So that is the idea behind what we are trying to get at later. We want to have a systematic way to develop these corrections, okay? And that is called the perturbation theory. Similarly, the eigenstate, the problem B, the nth eigenstate should be rather close to the eigenstate of the solvable problem A, and we would like to find the corrections due to this rough problem, bottom of the well, okay? Again, for this problem, the difference is in this inclined part of the potential energy function. So we are again motivated to see, perhaps there are corrections to the solvable problem due to this potential energy function in the middle relative to the known problem, okay? So the question becomes how to find these corrections in a systematic way. So we have good reason to start developing some approximation methods. Another example, we just mentioned that the harmonic oscillator problem is solvable. Okay, sorry. So this one is solvable. And you know two methods to do that, okay? Wonderful. Now, how about this? In addition to the oscillator, I have a quartic term. That will make the, the curvature even steeper. A quadratic term add to a quartic term, okay? Especially near the bottom part. Okay. Now you of course we know how to write down the Schrödinger equation right away. How to solve it? Okay. You can try operator method. You can try the wave function method, whatever. But it's not so easy to do. All right. But it's not entirely unhappy, you see. Okay. To make you more unhappy, how about this one? And this is the very important problem in physics, you know. Any two stuff, atoms, nuclear, neutron, proton, inside the nucleus, okay? Anything, or molecule, when they come together to form a bigger molecule, anything that may bind will experience such a potential energy function that I highlighted here as a function of the separation of the two entities. I mean everything that could bind. For two atoms, if they can bind, all right, first of all, when they are too far apart, they don't feel anything. That's why the U of X goes to 0 for X very big. Two atoms off by 1 centimeter, they cannot feel each other, right? Remember, the only atom you know how to solve hydrogen, ground state 1s, decayed with the Bohr radius, which is about half an angstrom. Okay, so half an angstrom, this other atom, half an angstrom, if they are 1 centimeter apart, one cannot feel each other's presence. The tail of the wave function already dropped to 0, practically 0 on the other side. So this atom does not feel anything from the other atom. Okay, so that's why very far away, don't need to be centimeter. Actually, if it is 10 angstrom away, it is already close to 0. But two atoms don't want to be too close to each other either, for various reasons. When they come to each other too close, the electrons will start to be too close to each other, and there is a Coulomb repulsion, obviously. That is the high school way of thinking. But now you are university year 3 student, okay? Another factor that usually is more important is that when the two atoms come too close to each other, the electron also gets too close to each other, and because they are fermions, they don't like to be too close to each other due to something called the Pauli principle. So one way or another, there are reasons that two atoms do not like to be too close to each other. Okay? The same goes to two neutrons inside the nucleus. And now, this is modeled by this part, okay, of the potential energy function. It rises steeply when the separation becomes too small, okay? It's like a hard wall, so-called. So you have 0 on this side, it goes up on this side. The negative here means it is attractive in this range. Otherwise, they will not bind, right? Repulsive will go away, all right? So they bind. So you have no choice, right? So the potential energy function must look something like that. And now, with a function that has a minimum, if you get close to the minimum, sufficiently close, you can expand it in Taylor expansion, and the first term will be parabolic, quadratic. So it's like a harmonic oscillator, but If you go slightly far away, it will be something like that. The parabola will not be perfect, okay? It is deeper on one side because the repulsion goes in this side, okay? It is shallower on the other side, okay? So now that is hard to do, right? So we know the Schrödinger equation, of course, okay? So again, we are motivated. Can we build some approximate solution starting with the known exact solutions of the oscillator? Can we develop these corrections in a systematic way? Okay, so these are the questions that we want to look into. Another example, I mentioned hydrogen atom. So you have solved this hydrogen atom Schrödinger equation with the Coulomb potential energy function, and then you know that the solutions are has a spherical harmonics theta phi part that goes into what you will call 1s, 2s, 2p, things like that. And then there's a radial part at the end, long expression. It is called the Lagrange polynomials. And then the allowed energies are the famous minus 13.6 eV divided by n squared. The minus 13.6 is this chunk of constants. So this is the known version, the solution, the exactly solvable problem. How about this? I mentioned spin-orbit interaction. We will explain more when we go into atomic physics. Nonetheless, I would like to flash the problem at you now. So the first two terms are the problem, give the problem that you solve exactly in the previous course. Nonetheless, there are additional terms, for example, spin-orbit coupling. Once you have this term, either you give up, say, I don't know how to do it anymore, okay? Or we try to use the known solutions, okay, that you solved last term and try to get at some approximation for the eigenvalues of this new hydrogen atom Hamiltonian with one more effect. Again, we need approximation. Let me just mention that 20 years ago, when I was teaching modern physics, quantum physics to COHK students, I don't need to do much about spin-orbit coupling. But suddenly, in the past 5 to 10 years, spin-orbit interaction has become very important in condensed matter physics. Now, experimentalists has discovered many materials with strong spin-orbit interaction that exhibit very fancy properties. Collectively, some of them are called topological materials, things like that, okay? And I would say the reason is that they like this class of material because it is a cheap way to get a magnetic field without buying a magnet, okay? So this spin-orbit interaction is like the orbital motion of the electron is generating, self-generating a magnetic field that interact on its own spin angular momentum. So you don't need to buy a big magnet, but then you enjoy the benefit of having the magnetic field in your sample, okay? And that makes much progress in recent years in condensed matter physics. So we will discuss this term particularly later. And there are more additional aspects on the hydrogen atom problem. For example, we apply an external magnetic field. Now we buy a magnet, apply it to a gas of hydrogen atom. What happens? Then your known solution only apply to this part of the hydrogen problem. But you have extra term called the Zeeman term. That is the Zeeman effect. Again, we have the exact solvable part with an extra term. We need some method to handle the extra term. Another problem, similarly, we incident light onto hydrogen atom. You know that light is EM field, right? So E, B, and propagating into U, okay? So, okay. How to do that? Okay? Continue. So, again, the electron has charge, the E field is oscillating, thereby you will have an additional term, the charge of the electron coupled with the oscillating E field. Okay? So you will have an additional term in the Hamiltonian. The scenario repeats. This part, you know how to solve exactly, but then you have an additional term. How to do it? Now, this is more difficult than the previous cases because we have time in the additional term. So we need another theory to handle this kind of problem. This is called time-dependent perturbation. This additional term is time-dependent. Okay? We will not do that at the beginning. We wait for a while when we talk about light-matter interaction. Okay? So we will do this kind of approximations, develop them as we go on. Now, let's get at some harder problems, okay? Helium atoms. Now, it should be very simple, right? Hydrogen, helium, lithium is the second element in the periodic table. Shouldn't be very difficult, right? So let's write down the Hamiltonian. How to do that? Just like any other problem, think classical, then go quantum, then you will get the Schrödinger equation, right? So you have one nucleus and then two electrons, 1 and 2, okay? So Hamiltonian is a function of position, coordinate, and momentum, okay? So you have this kinetic energy of electron 1, electron 2. You have potential energy of electron 1 and electron 2 when they see the nucleus, the Coulomb interaction between electron and nucleus. Then you have the two electrons interacting coulombically, the Coulomb interaction of electron-electron repulsion, okay? The potential energy function. So you have 1, 2, 3, 4, 5 terms. So kinetic energy of the two electrons, potential energy of the two electrons seeing the nucleus, and the two electron Coulomb interact, okay? So this is classical thinking. Go quantum, give operators to all this momenta and coordinates. Then you have this helium atom Hamiltonian, all right? Simple. We know the equation. That's the point I want to convey. And the Schrödinger equation becomes this, okay? The helium Hamiltonian, the wave function should be a function of the two electrons coordinates, R1 and R2. Solving this will give us the allowed energies for the helium atom as a whole. So it's formal, it's done. All the physics is done. The rest is how to handle it, okay? Again, you see the language. The energy E here refers to the energy of the whole helium atom. At this point, we don't have this notion or idea about there's one S state or atomic orbital for the electron, because those thinking refers to single electron states. We have a 2-electron system. The whole system consists of 2 interacting electrons and a nucleus. Okay, so this is the problem. So the case is that there's no exact solution. Okay, but don't feel bad. No one can do it exactly either. So you are not the only one. Okay, so now the question becomes, how can we understand helium and all the other atoms and the periodic table at the end? Okay, so that is really asking for some method to handle this very difficult problem. Okay, some students may wonder why it is hard. Look at this term. It is the electron-electron interaction part that killed the problem. Because this form, 1 over the distance, the separation, R1 minus R2 absolute value, you cannot do separation of variables. Okay, therefore, you cannot have a separate problem for R1, electron number 1, and electron number 2 separately. If you can do that, there may be a way to get at some exact solution. Okay, it is this interaction kill the problem and make it insolvable. All right. If you ignore this term and look at the other 4 terms, they don't cause problems, because if you take these 2 terms alone, it looks like a single electron 1 problem. If you take this other 2 terms alone, it is a single electron 2 problem. Fine. If you ignore the last term, everything's fine. Life will be easy, but no fun, okay? It will be boring, okay? But this interaction part makes the problem hard, but makes the world interesting. Okay, you have all kinds of materials that follows. All right, so that is the beginning of quantum chemistry. How we can still do something about this is unsolvable atomic problems. And for those students theoretically inclined, it is this kind of interaction term that leads to the big field of many body problems, many particle physics, some things like that, okay? If you look at the postgraduate courses this term, there is one on many body problem, and it is a course about handling electron-electron interaction in solids, in atoms, etc. But we will not do that here, okay? We will just discuss some big ideas about how that could be handled approximately. Even though we can conquer the periodic table problem, how about this problem? Molecule. What is the simplest molecule? H2. All right. What is the quantum problem? You have 2 nuclei. They may be 2 angstrom apart. So this distance may be 2 angstrom, okay? Then we have 2 electrons. Do we know the physics? We do. We know the equations, okay? So we can write down the Schrödinger equation. Kinetic energy for the nucleus number 1 nucleus number 2. Kinetic energy for electron number 1, electron number 2. All right. Now, electron 1 can see nucleus 1 and nucleus 2. So 2 Coulomb attraction. Electron 2 can see nucleus 1, nucleus 2, another 2. So 4 terms, fine, no problem. Okay. Now, nucleus 1, nucleus 2, Coulomb repel. Electron 1, electron 2, Coulomb repel. So we have 2 terms that are plus sign. Done. Bravo. Okay. Now, if you understand up to this point, do you follow me, guys? If you follow me in how to write down the Hamiltonian, congratulations. Okay. Your preparation is pretty good. At least, given a problem, you know how to write down the first equation, equation number 1. Then, only then, we can start thinking about, hey, this term is too hard to do. Ignore it for the time being. That term is ugly. Ignore it for the time being. What can we do with the simpler form? Okay? And that is the art of trying to develop approximations. Okay? Don't feel bad. Very few people, I don't know. This one cannot be solved exactly, I think. Okay? There's a problem called H2 plus. That is an ion, meaning if one electron is moved far away, okay, then we have an ion. Then we have fewer terms. We only have 1 electron, 2 nuclei, okay? That problem can be done analytically. That is the only molecular problem that can be solved analytically. But that is a pseudo-molecular problem. It's not a molecule, it's a molecular ion because it's charged, okay? Even that problem, if you solve it analytically, again, the physics is ugly. I mean, the solution has some funny function. We need to use cylindrical coordinates to solve it because you have 2 centers, okay? Not very nice thing to look at. So even you can do it, it's not very useful. All in all, in molecular problem, we cannot avoid making and developing approximations to gain some understanding of the existence, why molecules exist. And we will do that in the molecular physics part. So summary, I have given you many examples in different areas. Atoms, solids, say that part, harmonic oscillator binding part, okay? Molecules, that we have the situation like that. We have a real and interesting problem with a Hamiltonian that we can write down, but inside which we see some part, usually a big part, like the hydrogen atom part, plus a field term. A field comes in, interact with the charge. So that hydrogen atom alone part is the big part of the problem that can be solved. We will call that H0. The subscript 0 usually means it is solvable. That's the solvable part. We know the solutions. By that we mean we know the eigenstate, we know the eigenvalues, okay? And then, unfortunately, there's usually an extra part. This extra part make this whole problem H cannot be done analytically. Okay, make it hard to solve. Now the question becomes, we need some methods to treat this extra part H prime. We will call this part perturbation. 圍繞啊，圍繞啊。We will call this H prime part the perturbation to the exactly solvable H0. We want to develop some way to handle this extra part, to look for how this part, H prime, correct the known answers to give approximate answers to this interesting problem in hand. All right, so that is the big picture of many problems that we are going to discuss in our course. Okay, so I have given you many examples that we will go deeper along the way. So the art here is to explore how far we can understand atoms, molecules, nuclear solids, which are unavoidably and intrinsically many particle quantum mechanics problems, by not doing the many-body problem, by avoiding the complexity of solving many particle problems. We will stick to as much single particle solutions as possible and see how we can still understand a lot of physics, a lot of phenomena, experimental, observed things by making approximations. So in my mind, it is really street fighting quantum mechanics, but with elegance, okay? We are not fighting with random, chaotically with our techniques. We try to build up a set of logic or way of thinking to handle such problems. Okay, so it will be fun, I think. Okay, I have fun throughout the years preparing and teaching this course. So I hope that along the way you will enjoy the course. Okay, so I will stop here today. I will stay behind. Discuss with you if you have things to ask.